Cool. Okay. Gordon, all that. Okay, so this is going to be test four. Coming near the end now, there's just this, and then you have your one other test. Um, this particular, these two particular chapters are very different. So I found in the past that it's easy to get confused because we have all this stuff with circuits we're doing, and you finally get used to potential and current resistance and all that stuff. And then you get thrown into magnetic fields. So I'm gonna hopefully try and just lay everything out for you first and foremost so you see all the things you've learned, why you've learned them. Um, Hopefully just so that everything's a little bit more organized in your head. For chapter 28 in particular, I'm going to do more example problems than I usually do. The reason for that is because chapter 28 doesn't have a lot of complicated formulas or ideas, but it's how you apply them that's really hard. So you might have found in your homework when you did Kirchhoff's laws and stuff, there's a lot of small things that might trip you up. So I'm going to go through, especially for chapter 28, not so much here are the equations, but here's how you apply them. And then for chapter 29, it's more straightforward what I usually do. Any questions on that? Again? All right, well, let's kind of get into it. So, chapter 28 is fundamentals of circuits. In particular, we're looking at DC circuits. So, all DC means direct current. It just means that for all the circuits we're looking at, for everything we're doing right now, we're going to have a constant current. So, I or current is always going to be constant for us right now. And then for the most part, we're all looking at ideal circuit elements. And when I say ideal, I just mean other than the internal resistance of the batteries that you kind of touched on, stuff like resistors, capacitors, all that, they're going to act in an ideal way. Cool. All right. So first things first, I just kind of want to get you used to how to analyze a circuit. And when we say analyze a circuit, what we mean is for every single circuit element, we want the potential difference across it and the current going through it. So I'm going to start with sort of how you actually draw current. So I have a battery up here with two resistors. So this is just a common series circuit. So what I'm going to do here is the current we usually say comes out of this positive terminal and then goes back into the negative end. So when I draw my current, I'm just going to call it I. And this is one good way to start drawing the direction of your current. One thing I want to note here is that you're going to have only one current per wire in your circuit. One current per wire. A lot of people get confused because they see this wire and they see I have resistors here, I have a battery, don't I have as much as three wires? And you always want to notice it doesn't matter how many circuit elements you have on a wire, it only matters if there's a junction. That's what defines if it's an independent wire. So here on this circuit, I have two resistors and a battery, three circuit elements total, but I only have one wire, which means there's only one current in this circuit. For this one down here, where we have two resistors in parallel, I can draw my current similarly. Here's my current I coming out of the positive end of the battery. I reach a junction, and all a junction is two or more wires split. That's kind of a bad way to put it, but it's either a junction or a node. It's going to look something like this. The point is when current reaches a junction, it's going to split. So we have our current I it reaches this junction, and it's going to split into I1 and I2. Notice they're going to come and reach this junction, and then they're going to come back and reconstitute into the current I. Cool. So one thing I want you to note, this top circuit is only one wire, even though it has 3 circuit elements, and so there's only one current in this entire circuit. So 1 current per wire. There's 1 current in this circuit. Here on the bottom, we have, this is 1, 2, 3 wires. So we should have 3 currents. 3 wires, 3 currents. So I know it's kind of simple, but it's helpful when things get a little bit more complicated to literally sit there and see, okay, how many currents should I have? How many wires are here? So it's just good practice. Any questions? Okay. I'm going to look a little closely at this junction here. So I told you when a current flows into a junction, it's going to split. There is something very special that happens there. So because charge is conserved and all current is charge per unit time, that also means current is conserved. So we have this rule called Kirchhoff's current law, and it says that the current flowing into that junction must equal the current flowing out. And how we write that mathematically, so this is Kirchhoff's. You're going to see it as either current law or node rule, something like that. It's just the sum of the current coming into that junction has to equal the sum of the current coming out. And it makes sense because, again, charge and current must be conserved. So if you wanted to see an example, up here, we have our current I flowing out of the positive end of our battery. It reaches this node and splits off into I1 and I2. The current flowing into the battery, I can see is going to be just I. And then the sum of the currents flowing out is going to be I1 plus I2. Cool. So that's an example how you use it. And let's put a little star here. Okay. One more thing before I move on, and it's a notation thing. So what you can do when you analyze a circuit is you can write all these arrows. So I have an arrow for this current I have an arrow for I1 and I2. There's a simpler way of doing it and a way that I like a little bit better. So instead of writing, say, this arrow I1 pointing down, I'm going to write a positive and negative sign on my resistor. And I'll explain in a little bit. There we go. So, and then I'll just write that that's I1 and that's I2. So this notation I like better because when you use Kirchhoff's current law or loop rule, which we'll talk about in a sec, it ends up making the problems a whole lot easier. But I just want you to know that it's just notation. So if I have a resistor here, and I'll just draw one. If I have a resistor, I can either write this, the current is flowing to the right, or I can write a positive and negative sign. All that's saying is current flowing through resistor is going from positive to negative. So this is notation. Notation, there's no physics behind this at all. I said I want the current to flow to the right, and I said another way of writing that is the current going from positive to negative. So it's just notation. It's how I like to write it, and you're going to see that it ends up making the math a little easier down the road. Cool. All right, so all this was an introduction to what is a circuit, how to count wires, sort of what things look like, how to draw your current, what is current, and then also sort of an introduction to Kirchhoff's current law. After that, we have the idea of equivalent resistance, which you've seen quite a bit. So here I have what's called a series circuit. So all that is we have two resistors that share the same wire. So in that situation, if we wanted an equivalent resistor, we would just say our equivalent is the sum of all our resistors that are in series. So in this case, it's R1 plus R2, but if I have more, then I can just add those as well. So it's pretty straightforward. If I have two resistors in series and I want to create an equivalent resistor, then I just add them together. Some things to keep in mind for resistors that are in series. They're going to share the same current. But have different potential difference across them. So to write that out, if there's a current I flowing through here, you can kind of see it easily. Remember how I said there can only be one current per wire? We only have one wire in this circuit, so we only have one current. So the current going through R1 has to equal the current going through R2. So current going through R1 equals current going through R2, and that just equals the current in the entire circuit. When it comes to potential, the potential difference here across resistor 1 and potential difference across resistor 2, they do not equal, but they do add up to equal the potential of the battery. So you might have seen this in class written as, if delta V is the potential of my battery, that's just going to equal the potential difference across my first resistor plus the potential difference across my second resistor. So if you have to remember anything, remember how to add up equivalent resistors like this. And then remember for resistors in series, they're going to have the same current and different potential. Now, our second case is when we have parallel resistors. So they're going to be on different wires. And you can kind of see here, if we draw our current, it kind of tells us a little bit. So we have current coming out of the battery. I'm going to call it I. It's going to reach this node here. And whenever current reaches a node, it's going to split into two. So here's I1, here's I2. And again, I like my notation a little better, so I'm just going to put it there. So we can see for resistors in parallel, they're going to have different currents. So for resistors in parallel, they're going to have different current, but they're going to have same potential. So they're opposite of the resistors in series. If I was going to write that, all I'm saying is that the potential difference across R1 equals the potential difference across my resistor 2, and that equals the potential difference of the battery. Similarly, the currents aren't equal, but they do add up. So the current of the circuit I is equal to I1 plus I2. Notice that this here is just Kirchhoff's current law. So that's how we ended up getting that. You can see it right up there. And lastly, if I wanted to add up these resistors and create an equivalent resistor for this parallel situation, it's just 1 over R1 plus 1 over R2 to the negative 1. By the way, it's really important if you're not super used to using your calculator for this sort of stuff, just make very sure that you're adding up these fractions and then inverting the entire thing. A lot of students get tripped up on that, and it's a really small thing to get tripped up on, especially if you know the physics. Okay, let's see. So that takes us into voltage. So we looked at our equivalent resistances. We only have two cases, resistors in series or resistors in parallel. As you know, things get more complicated. So we're going to see, again, we're going to focus more on how to apply this, but this is just an overview. And we looked at Kirchhoff's current law up here and sort of how to draw current in a circuit. So now we're going to go to Kirchhoff's voltage law. So this is one of the more important ones. All it says is that the sum of the potential difference of each circuit element, of which let's say there are I circuit elements in your circuit, the sum of all those potential differences in a closed loop have to equal 0. So this is the equation, but I like kind of writing it out. So again, sum of the potential differences across each circuit element in a closed loop is 0. Cool. Now, when I just say that, it sounds pretty simple, but as you probably found on the homework, when you go to apply it, there are some pitfalls. So I'm going to focus now on just a couple examples of how to apply Kirchhoff's laws and in general, just when you see a circuit, how to find the current, how to find the potential. So here's an example here. Um, Now this is a pretty simple circuit, so you might see that you could use equivalent resistance here and you can add up these two parallel resistors and solve it that way. Totally fine to do it that way. And I would encourage, if you like it and if you have a very simple circuit, go the equivalent resistance route. Um, but when we get to say this one example 2 down here, you definitely want to make sure you're comfortable with Kirchhoff's law. And in general, my rule is if I see more than one battery, I always use Kirchhoff's law. If I see one battery, I'm going to try and use equivalent resistance first. But I'm using this very simple circuit just as a way of getting you used to Kirchhoff's voltage law. Um, okay, so step number one, step number one is we're going to choose the direction of current for each wire in the circuit. So already, whenever you see that in the book, it seems really obvious. So when I say choose the direction of each current, you do have to keep some things in mind. For one, again, there's only one current for one wire. And so count the number of wires you have, count how many currents you have, and then assign one current to one wire. That's the first thing. So I can't have two currents for one wire. The other thing is I really can choose any direction I want. What's going to happen if I choose the wrong direction is, so if I choose the wrong direction, all that's going to happen is I get a negative current. So wrong direction, negative current. And if I see that negative current later on in my calculations, all I'm going to do is I'll flip the direction. So I'll say, okay, my current wasn't pointing down. It turns out it was pointing up. So that's all you'll do. So let's choose the direction of our currents. So it looks like we have 1, 2, 3 wires here. So we have the wire that has the battery. We have one wire with the 10 ohm resistor and then one wire with the 20 ohm resistor. Again, I'm counting the wires because I see a node here. So I like to start with the battery and I like to draw the current out of the positive end. It's just, you don't have to do it that way. It's just kind of a habit. So I'm going to draw the current here if I can. I'm just going to assign this a value of I. Then my current I is going to split into two. I'm going to call this I1 and I2. And then the current I comes back into our battery. Okay. So again, I'm going to write my notation for the direction of each current now that I have them labeled. And again, I2, I1, they could be totally the wrong direction. I chose them literally based off of nothing. I just wanted to say, all right, down and down. I could call them both up. It doesn't matter. So again, like I said before, instead of drawing this current going down, I could just write it's going positive to negative. And then this one is going down, so positive to negative. Again, it's a notation choice, and you'll see why I like it in just a second. So all I did so far is I assigned a current to every single wire in the circuit, and I just arbitrarily chose a direction, and I put the notation that I like in there, my positive and negative signs. So next step is we're going to choose the direction of our loop. Direction of loop. So this loop can be clockwise or counterclockwise. Um, Here's another thing that slips through the cracks often with students. If there are multiple loops in the circuit, which in this case we have two closed loops, whatever direction I choose to go in, clockwise or counterclockwise, I have to stick with that. So yes, you can choose counterclockwise or clockwise, doesn't matter. But once I make that choice, I have to stick with it. So a lot of times I'll see students choose different directions for each loop, and then they'll get some crazy answers. So that's one thing that I think slips through the cracks, and I'll just write it here. Again, once you make that choice, once you make choice, all loops must be in the same direction. Cool. So, it doesn't matter which way I choose, clockwise or counterclockwise. For me personally, I guess I'm just gonna go clockwise because I feel like it. So I'm gonna draw my loops. I'm gonna say we're going clockwise for both. And there we go. So now everything is set up. All we gotta do is follow Kirchhoff's voltage law. So it says that if I sum up all the potential differences of every single circuit element in a closed loop, then they should equal 0. So I'm going to start here, and I'm going to literally pretend like I'm walking around this loop clockwise. So I'm starting here, I'm walking. I reach my battery, and my battery is taking me from negative to positive. So it's increasing my potential. That means that is a positive potential difference. So that means that is positive 12 volts. That's my first potential difference. I'm going to keep walking. I get to my 10 ohm resistor here, and it looks like it's taking me from positive to negative. So it's subtracting my voltage. So that means that is a negative potential difference. So I'm going to write negative, and I'll write it right now as the potential difference across the 10 ohm resistor. So that's negative delta V of the 10 ohms. And I'm walking, and I get back to where I started. So I completed one closed loop. I can set all those potential differences equal to 0. So you'll see that it's really the positive and negative signs that kind of get you. And that's why I really like my notation of writing the direction of the current, because whenever you go from plus to minus, you just slap a negative sign on that potential difference. Anytime you go from minus to plus, that's a positive sign on your potential difference. So that's why I like that notation. It's really good for Kirchhoff's voltage law. Does anyone have any questions? I'm just going to pause for a sec. Cool. All right, I'm just going to keep going then. So we have two independent loops here. I did one. Let's do the other. So again, I'm going to start wherever I want. Let's say we just start down here. I'm walking clockwise. I reach my 10 ohm resistor and it's taking me from minus to plus. So that means it's increasing my potential. That is a positive potential difference. So that's positive delta V of the 10 ohm resistor. Walking. I reach my 20 ohm resistor here. It's taking me from plus to minus. It's decreasing my potential, so that is a negative potential difference. And that'll be the potential difference across the 20 ohm resistor. I'm back to where I started, so all those potential differences equal 0. Cool. So these here are going to be, they're sometimes called loop equations. They're basically the set of equations that we found by Kirchhoff's voltage law that are going to help us find the currents, the potential differences, and everything we want to know about the circuit. So first things first, we don't know the potential difference across the 10 ohm and 20 ohm resistor, but we do know some stuff about current and we know some stuff about resistance. So we need a way of taking a potential and turning it into something about current and resistance. How we do that is we're going to use Ohm's law. So that's kind of the last piece of the puzzle, Ohm's law. And all that is your potential difference across a circuit element equals the current through that element times the resistance. And this is only for resistor, sorry. Only for a resistor. Cool. So I'm going to change my equations here, substituting in Ohm's law. So we have 12 volts. Now the current going through my 10 ohm resistor is I1. And then the resistance is 10 ohms. That equals 0. So again, potential difference going through the 10 ohm, that's I1, 10 ohms. The current going through the 20 ohm resistor is I2. So that's minus I2 times 20 ohms. Cool. So now my goal here is I want to find what current 1 is, and I want to find what current 2 is. So it's pretty simple. Equation 1 up top, we can just already solve for. So if I just add I1 times 10 ohms on both sides, get I1 times 10 ohms equals 12 volts. And then I'll just divide by 10 ohms on both sides. So that's 12 volts over 10 ohms. And that is 1.2 volts per ohms is amps. And that's the SI unit for current. So notice how my current I1 is positive. That means I chose the correct direction. I don't have to do anything. Now that we know I1, I can stick that in here. So we got, I'm going to put in the fraction just because I see that the 10 ohms will cancel. So plugging in 12 volts over 10 ohms for I1. Now multiply that by 10 ohms. And then I'm going to add I2 times 20 on both sides. So here's current 2 times 20 ohms. Divide by 20 on both sides. So this 10 is going to cancel. That's 12 volts times 10 ohms, sorry, 12 volts divided by 20 ohms equals I2. And then that's 6 volts over 10 ohms. That's so funny. I'm really bad at this. 3 over 5. I'm just going to leave it as 3 over 5 amps for I2. And notice that my current is again positive, which means I chose the correct direction. So I found I1 and I2. If I wanted to find my big current I here, that's when I would use Kirchhoff's current law. 0.6, thank you, Jillian. I'll just write 0.6, so that's nice. Okay. Alrighty, so notice in this node up here, the sum of the currents going in has to equal the sum of the currents going out. So I'm just going to write here, my big current I is going in, I1 and I2 are going out. And we know that that's true because both of our currents, I1 and I2, are positive, so we chose the right direction. One thing that you're going to want to do is, when possible, use Kirchhoff's current law last, or only use it when you know the direction of the current, because if you use it and you don't know the correct directions, you can mess up. So that's why I kind of like to save the current law for the last step. So I know this is true because I know that current I1 and I2 are for sure the correct direction. And if I add them together, I'll get my big current I. So that's just 1.2 amps for I1 plus 0.6 amps for I2. So that means my big current I is 2 amps. Cool. So I got all my currents here. And if that's what the problem asks for, we got it. And that's hilarious. Thank you. 1.2 plus 0.6 is definitely 1.8. Sorry. I really just saw what I wanted to see there. My bad. My bad. It's 1.8. I saw what I wanted to see. My fault. Does everyone get how I got 1.8? Sorry, I didn't mean to confuse by saying 2 amps there. Okay, does anyone have any questions? Okay. So that was our first example. It was kind of simple. And again, in real life, if you see one battery and two resistors in parallel, it's probably just going to be easier to use equivalent resistance. So I'd go that route. Um, Here's an example where we have two batteries and we can't use equivalent resistance. So here you're going to have to use Kirchhoff's current law. So let's just do this one quick, and then we'll get into the last little bits of chapter 28, and then we'll move on to chapter 29. I realized I was going really slow. Okay. So I see this. This was a problem in your homework. Again, first thing I'm going to do is I'm going to choose a direction for the current. So one thing that's really funny here, really complicated looking circuit, but remember I said it doesn't matter how many circuit elements I have. If they share the same wire, then there's only one current per wire. So this actually, even though this looks really complicated, there's only one current flowing through this whole circuit. So I'm going to say it flows clockwise just because for me personally, I see that this is a 9-volt battery, so I feel like it's going to overpower the 6-volt battery. Again, absolutely doesn't matter. I could choose the other way, and then if I'm wrong, I'll just get a negative sign. So again, step one, how many wires do I have? How many currents do I need to assign? There's only one wire, so I assign one current. And the direction of that current doesn't matter. So I'll just put some direction. Some students get tripped up on this little part here. So this is what's called ground. Um, this is not a node. So current is not splitting here. Um, all this ground sign, it just means that at this point, potential equals 0. So that's there in a problem just in case. I think this problem asks what the potential is at A and B. So you do need a starting point, and they need to tell you the potential somewhere on the circuit for you to be able to tell anything other than just potential differences. So I hope that makes sense. There's only one current in this circuit, even though it looks really complicated. Cool. So step one, got my current. Now, again, notation wise, instead of just writing this direction, I really like my positives and minuses. So for this 2 ohm resistor, instead of current going to the right, I'm going to say, I'm going to put in this positive and negative sign. That tells me it's going to the right. For this 1 ohm resistor, current's going to the left. So I'm going to write it's going from positive to negative. And again, really easy when we do the Kirchhoff's current law or voltage law. Cool. Got my currents in there. Now let's get our loop. I'm going to stick with clockwise. Again, we can choose the direction. Clockwise just feels good today. So we chose our currents, we chose our loop. All that's left to do is to basically walk in a circle. So I'm going to start, let's say here, and I'm going to walk clockwise and add up every potential difference of every single circuit element. So it looks like I'm walking, walking, walking. My 9-volt battery is taking me from negative to positive. It's increasing my potential. And so that is a positive potential difference of 9 volts. I keep walking. My 2 ohm resistor is taking me from it's taking me from positive to negative. So that is a decreasing potential difference. So I'm going to put a negative sign there. And it is decreasing by a potential difference of the current going through it, which is I, times its resistance, which is 2 ohms. I keep walking. Now, my 6-volt battery, as I'm walking clockwise, is taking me from positive to negative. So that is a negative potential difference. So I'm going to add a negative 6 volts. Again, that's why I like these positives and minuses, because it's really easy to keep track of. Okay, I'm going from plus to minus, or I'm going from minus to plus. All right, last one, I'm going to keep walking. I get to my 1 ohm resistor. It's taking me from positive to minus. So that is a negative change in potential difference. So I'm going to add a negative sign, and that is negative the current going through it, which is I, times its resistance, which is 1 ohm. I get back to where I started, and I know that throughout an entire closed loop, if I add up all those potential differences, they have to equal 0. Cool. So this one's pretty simple. We just have one thing to solve for, just one current throughout the entire loop. So 9 minus 6, that's going to be 3 volts. And then negative 2 minus 1 is negative 3. So that's negative 3 ohms times I. I'm going to add 3I on both sides. So that's 3 volts equals 3 ohms times current. Divide by 3. So that's 3 volts over 3 ohms, which is 1 amp. Notice my current is positive, so I chose the right direction. I don't need to change anything. And the current is just 1 amp. So in this problem, just for your information, if they were to further ask, say, what is the potential, let's say at B, point B right here. So all I got to do is I do need to follow the direction. So I need a starting point, an ending point, and I need to walk in the same direction that I put my loop in. So personally, I'm going to start here at potential equals 0, just because that's the only point where we actually know what the potential is on this circuit. So I'm going to start there. I'm going to walk around, walk around, walk around. It looks like my first potential difference is my positive 9 volts. So how I like to do this is I start at 0. I have 0 potential. Then I add 9 volts. Then I'm going to take away, because this is a negative potential difference, I'm going to take away 2 ohms times 1 amp, because I know what my current is now. This is the potential difference across the 2 ohm resistor. Then I keep walking around. I'm going to take away 6 volts, and then I get to B. So it looks like if I add everything up, 9 minus 6 is 3 volts, and then 2 times 1 is 2, so that's minus 2 volts. So it looks like the potential at point B is 1 volt. Yeah, cool. So I hope that made sense. That's kind of how I like to think about it in my head. Any questions on that? Cool. Okay. So everything here was basically just to show you how to use Kirchhoff's law. Things are going to get more complicated. You're going to see bigger circuits, but as long as you follow this to a T, count the number of wires, assign a current to each wire, choose a direction, stick with it, choose your loop direction, stick with it, and then do it this way, then you should be all good. Um, Next is going to be power in circuits. So this is sort of at the tail end of chapter 28. So all it says is we're going to have a power supplied by the battery. And that's just going to be, it's usually written as P bat, and that equals the current coming out of the battery times the EMF, where EMF is just the potential difference of the battery, just fancy word. So simple equation is also the power dissipated by a resistor. So a resistor basically it resists the flow of electrons, so you're going to get some heat. That heat dissipates the power supplied by the battery, and the amount that it does is going to be equal to, I like this way, is going to be equal to the current squared through that resistor times the resistance. And if we use Ohm's law, we can actually change that to the potential difference across the resistor squared over R. So these are the equations that I like to use. Cool. Okay, so real quick, this isn't too much, but I just kind of wanted to show you. Your professor really likes rank the brightness on his tests. So you might have seen it on the practice test. You'll most definitely see it on the real test, but if you understand it, it's going to be a quick question, but there are a couple pitfalls that I just want to briefly go over. So, first of all, when you rank the brightness of these light bulbs, this whole thing, you're going to be using power. So, as soon as you see light bulbs, I want you to think, okay, let me use power. The other thing is these light bulbs are identical, And basically, we're going to assume that they're just resistors. Assume that they are resistors. So they basically just act like resistors. And treating them like resistors makes the math a little bit easier. Okay. So let's say we want to rank the brightness of these two bulbs here. So we have a bulb A and bulb B, they're in series. I'm just going to pretend these are resistors. And so let's say we want to make an equivalent bulb or equivalent resistor here. If I have two resistors that are in series, here we go. If I want to make an equivalent bulb, I'm just going to add the resistors together. So I'm going to start, I'm going to call this R equivalent. There's a current I flowing through here. And R equivalent just equals the resistance of A plus the resistance of B. We just assume they're identical and they both have resistance of R. So R plus R, so that's 2R. So far, so good? Okay. So first step always for me, even if you feel like you have a handle on it, is simplify it down to as simple a circuit as you can. So here I had a series circuit and I simplified it down using my series rules to get it to be one bulb. So that's kind of step number one for me. Step two is whenever I rank the brightness, brightness is just the power dissipated. So I'm going to use one of these equations up here. Doesn't matter which one I use. What does matter though is once I make a choice, like let's say I use v squared over r, I'm going to want to stick with that. If I use I squared times r, I'm going to want to stick with that. One thing that happens with students is they'll switch up which equation they use mid-problem, and then they'll get confused as to what they're even looking at. So my one piece of advice is, doesn't matter which one you use, but once you make that choice, you have to stick with it. For the sake of this problem, I'm going to use I squared times r just because that's the one I usually prefer. So that's this guy right here. So there's a few ways you can do this. Trying to see what's the best way. We could start by just writing the power dissipated by this equivalent light bulb, let's say. So the power dissipated by that light bulb is going to equal the current going through it, which is just this big I, so I squared, times its resistance, which is R equivalent. So that's the power dissipated by this light bulb. Cool. Now, if I go back to my series circuit, one thing I note is that when light bulbs are in series or when resistors are in series, they don't have the same potential difference, but they do have the same current. So if I was to say, write the power dissipated by A, that's going to be whatever current is flowing through it, IA squared, times its resistance, which is just R. The power dissipated by B is IB squared times R. Now I know that the resistance through A equals, I'm sorry, the current through A is equal to the current through B, which is equal to just the current through the entire circuit. And again, that's because we have one wire here, we have one current, and we also know that resistors that are in series have to share the same current. So you can kind of see this, but if IA equals IB equals I, this is just equal to I squared R. This is equal to I squared R. So it looks like the power in A, or dissipated by A, equals the power dissipated by B. And so they have the same brightness. Same brightness. Cool. Any questions on that? Okay. Some of you might have just seen that immediately, but I really think it's worth going through because it's really easy to just make it a little more complicated than it needs to be. Do, 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 do. Okay. Okay. Um, you know what? For the sake of time, I'm just gonna skip these two for right now, the parallel and the mixed case. I'll do them in the notes just so you can look at them later, but I just want to make sure we get to magnetic fields. So, okay, I'm gonna leave that for right now. Um, last part of chapter 28 is RC circuits. So all RC is, that just means it's a resistor capacitor circuit. So there's some very special qualities to a resistor capacitor circuit. So if you remember, a capacitor stores charge, so it can actually be charged up, and a resistor dissipates charge, so it can actually take charge from the circuit. What that means is we can describe some equations for how charge will build up on a capacitor versus how it will discharge on a capacitor. So for these, they're just equations. I'm going to put them here. Know them, know when you see a specific problem, how to use them. So for a situation where we're charging a capacitor in an RC circuit, the charge on the capacitor as a function of time is just going to be Q naught, the initial charge, times 1 minus e to the negative t over tau. So this is charge as a function of time, or instantaneous charge. It has units of coulombs. This is the initial charge, if there is any on the capacitor, initial charge. They'll usually specify. If they don't specify an initial charge, just assume that that's 1. So this is an exponential. T is time. And then tau is our time constant. So that's our RC time constant. Basically, tau is equal to the resistance in your circuit times your capacitance. All that says is basically how much resistance I have in the circuit and how much capacitance will determine how fast or slow my capacitor can charge or discharge. That's all this is saying. It's kind of a constant of proportionality that tells you how much this is going to either decay or charge by, how quickly it's going to do that. Cool. So that's charging. Here is discharging, which you're going to see a lot more. So again, we have the charge on the capacitor per unit time is going to be equal to the initial charge, so whatever you start with, times e to the negative t over tau. Again, t is time, tau is your time constant, which is resistance times capacitance. Cool. So again, this is kind of a situation where the equations are what they are, but actually using them is a different story. So let's do an example. Okay, so we have a pretty complicated circuit here. So everything's charged up. The switch closes. So now our capacitors and our resistors are connected. And slowly those resistors are going to be taking charge away from the capacitors. And we want to know basically at what time has, let's say, the current in the 8 ohm resistor decayed to half its original value. Let's start there. Okay. So first thing you want to do with any of these problems, if I see a huge complicated thing, I'm going to use my equivalent rules and just take it all the way down to an equivalent circuit. So just as a reminder of our equivalent rules, when we got series, which is just two circuit elements sharing the same wire. For resistance, we're just going to add them up. So R equivalent for series is just R1 plus R2, etc. For capacitors, it's different. It's going to be 1 over C1 plus 1 over C2, etc. to the -1. For parallel, which is just two circuit elements on different wires, if I want equivalent resistance, it's going to be 1 over R1 plus 1 over R2, etc. to the -1. And our equivalent capacitance is going to be C1 plus C2, etc. So basically, resistors and capacitors are just flipped in the two situations. So first things first, I'll start with my capacitors here. I see I have two 60 microfarad capacitors here, and they're sharing the same wire, so they're in series. So I'm going to use my series rules and combine those. So here's just a drawing. So I'm going to combine them here. Let's call that like C12. This is our 20 microfarad. So I want to basically add these two 60 microfarad capacitors together in series. To do that, my series rule is 1 over capacitance 1, which is 60 microfarads, plus 1 over capacitance 2, 60 microfarads, and that is to the -1. Cool. So that's capacitance 1, 2. Now, once I make that, I see I have my equivalent capacitor I just made is now in parallel with my 20 microfarad capacitor. And if I look at my parallel rules for adding capacitors, all I got to do is add them together. So that's C12, if I want C equivalent, that's C12 plus 20 microfarads. Putting that together, that's this whole ugly thing plus 20 microfarads, which I think I have somewhere is 50 microfarads. Cool. So I made an equivalent capacitor. Now let's make an equivalent resistor. So I see that I have my 30 ohm and 20 ohm resistors. They're in parallel. I'm going to look at my parallel rules. Looks like I got to do this thing. So let's call it R12. Here's our 8 ohm. Here's R12. When I add up two resistors in parallel, it's going to be the first resistance, which is 30 ohms, plus the second resistance, 20 ohms, everything to the -1. Once I add those together, I have that equivalent resistance in series with an 8 ohm resistor. So I can just add them together based off of my series rules for adding resistors. So our equivalent is just 8 ohms plus R12, which is 8 ohms plus this whole thing, 1 over 30 plus 1 over 20 to the -1. And that is, you can do the calculation yourself, but that is 20 ohms. So once I get all my equivalent capacitances and resistance, I like to just draw out my circuit one last time as it is now. So here's C equivalent, here's R equivalent, and we know that C equivalent is 50 microfarads, R equivalent is 20 ohms. Cool. So my question up here says the capacitors are charged, then the switch closes. So what that tells me is they're charged, and now that the switch closes, current and charge is flowing through the circuit. It's flowing through those resistors, which means it's dissipating. That means we're discharging. We're taking charge off of our capacitors over time. So I'm going to use my discharging equation. So discharging, I'll look it up in my formula sheet. I see that the charge per unit time, or as a function of time, is Q naught e to the negative t over tau. Cool. Oh yeah, I forgot about this. There's an equation here for charge, and I actually forgot to put the equation for current, so I'll just put it in. If you want to find it, just basically take the derivative of charge, because I is dq dt. So if I want the current per unit time, it's negative initial charge over resistance times capacitance, e to the negative t over tau. Cool. Awesome. So I want to know at what time has the current in the 8 ohm resistor decayed to half. First, we don't. Okay. So I'm going to start with, we have our C equivalent, R equivalent. I'm going to find the time constant. So tau, can everyone see my screen? That's definitely my connection. My bad. Can you guys hear me? Okay. Sorry about that. Yeah, I have terrible Wi-Fi. Okay, cool. Okay, so just finishing this question out, equivalent resistance is 20 ohms, and then multiply that by my equivalent capacitance. So that's 50 times 10 to the negative 6 farads. One thing is you want to keep this in ohms times farads. That's how you get your per unit second. So 1 over seconds. So since I had a micro there, I'm going to put that out. And it's hilarious, I don't have a calculator. Pretty sure that I'm just going to leave it as 1,000 times 10 to the negative 6 seconds to the negative 1, just for right now. Cool. In the problem, I forgot to also say, they do specify that the potential difference across the capacitor is 10 volts. So that is going to be important. The reason being is I want to find what the initial charge is on this capacitor. To do that, I'm going to use our old Ohm's law, which is C equals Q over V. So it's hilarious. There's two Ohm's laws. There's one for resistance and there's one for capacitors. The one for resistance is our IR. So that's for resistors. Ohm's law for capacitors is your C equals Q over V, where Q is the charge on your capacitor and V is the potential difference across it. So if I want to know my Q naught, it's just going to be my total capacitance, which is 50 microfarads, times my voltage, which is 10 volts. So that's just going to be 500. I'm going to leave the micro in there. So that's 500 microcoulombs. That's my Q naught. So I'm going to use the discharging equation for current. So that's current as a function of time is going to equal, go up yaw, negative Q naught over RC. So negative Q naught over RC e to the negative T over tau. Okay, cool. Mhm. Okay. Sorry, I'm taking so long to do this. Okay, so the specific time they want us to find is they want to say, okay, at what time has the current in the 8 ohm resistor decayed to half its original value? Okay, so it's kind of hilarious. We actually don't need to find this value. Don't need. And that's because I totally didn't see, but what we can say is the current at some time is just the initial current times e to the negative t over tau. And then all we want to say is at some time, at some day to half in here, at some time of our, we have 0.5 equals e to negative t over tau. Now, if I want to solve for t, all I have to do whenever you have exponentials is take the natural log of both sides. So I'll take the natural log here. Now, when you have the natural log of e to the something, it just equals that something. And that's because whenever you have an exponent in a natural log, you can put it in front. So that ends up being x times ln of e. And then ln of e is just 1. So that's why that works. So ln 0.5 just equals whatever my exponent is, which is negative t over tau. So my time is just negative tau, ln 0.5. So I'm just gonna, I also don't have that in the calculator. So I'm just gonna write it as do 20 ohms times 50 times 10 to the negative 6 farads. There's a negative sign times ln 0.5. Oh yeah, the 0.5 came from this the question, and this is just basically one example. It said at what time has the current decayed to half its original value? If I wanted to write what that means mathematically, I'm just saying the current at some time, so I of t is now half of its original value. So it's 0.5 times I naught. I'm again taking way too much time, so I'm just going to add an etc. there and move on to magnetic fields because I'm yapping way too much. Okay, so this is all chapter 28. So it's basically just a lot of it is Kirchhoff's law. You'll definitely see that on the test. So get comfortable with equivalent resistance, get comfortable using Kirchhoff's law. You want to make sure you want to make sure you understand it so that you can use it quickly because as you know, time is a little bit tough. Time is kind of tight on the exam, so make sure you're good with that. Um, I'm going to finish this in the notes, but ranking the brightness of light bulbs, make sure you're good with that. And then these RC problems, they're not tough. It's going to be something like this where you have a capacitor discharging and they ask for the time, something like that. Um, the biggest pitfall I'd say is if you have something complicated like this, make sure for your tau that you're using your equivalent resistance and equivalent capacitance. So you're going to use the entire circuit. So you got to make sure you use your equivalency rules. Um, that's basically it. And yeah, if no one has any questions, I'll just move to chapter 29. So let me know. Cool. Okay. So completely switching gears. We talked about circuits, all this stuff, all these rules. Now with this new concept, magnetic fields, I'm just kind of go slow. So magnetic fields is really it's tied in with electricity and magnetism. That's kind of why this course is called electromagnetism. So we started with the E field, electric force between two charges, all that stuff. One thing you'll notice, we never talked about moving charges at the start, and that's because whenever you have a moving charge, you have a magnetic field. So now we're really switching gears into charges are moving. You might say, because we have current, we now have magnetic fields we need to look at. So that's really the only change is now we have moving charges and moving charges create something called the magnetic field. And we kind of want to study what is a magnetic field? What does it do? So um, first thing is, and you'll use this for moving particles only. So if I have a moving point charge and it's moving through an external magnetic field, there's something we're going to call the magnetic force, or Lorentz force. So this is sort of the magnetic variation of Coulomb's force, which we did for electric field. So just to draw this, I have a point charge. Let's call it plus Q. Now we know that everything needs a velocity if we're talking about magnetic fields. So has some velocity here. And let's say there's a magnetic field that's uniform and it's pointing down just like this. So the magnetic force or Lorentz force that's acting on this particle is going to be written as FB, and it's a vector, so I'm going to put a vector sign. It's equal to the value of charge that my point charge has, Q, times its velocity crossed with the magnetic field. And I'll go into this. So again, this is a force. It has units of newtons. So this is the force acting on particle, units of newtons. This is the charge. So if I have a really highly charged particle, it's going to feel a large force. If I have a particle that's not charged very much, it's going to feel a very small force. This is the velocity of the particle in meters per second. Charge is always in coulombs. And then this is the magnetic field that it's going through. So magnetic field. And it has units of Teslas. which we note with a big T. Okay. And just a note here on this cross product, all this is saying is that the Lorentz force is perpendicular to the velocity, and it's also perpendicular to the magnetic field. So they're all at 90 degrees with respect to each other, which is why we're going to use our right-hand rules, which I'll explain in a little bit. So you'll use this equation. Um, he likes one particular problem where you have, let's say he'll say, there's a proton, it's going straight, and then there's a magnetic field like this pointing down, and he might say, what direction is the particle going to go in? So in that case, you're going to use your right-hand rule and Lorentz force here. Again, I'll kind of show you in a little bit specifically how to use the right-hand rule because I feel like there is a lot of confusion. A lot of people think there's like 5 different right-hand rules. There's only one, and I'll show you how to do it, and it'll be all good. So yeah, that's Lorentz force, similar to Coulomb force for electric fields. Now, just to touch on the magnetic field here a bit. So again, we note it with this B here. It has units of Tesla, units of Teslas. Now, there's a very specific way of finding the magnetic field due to a moving point charge. So the Lorentz force is the magnetic force acting on a particle that's in a magnetic field. When a particle is moving, however, it actually creates its own magnetic field. And if you want to find that, you use what's called the Biot-Savart law. So you are not going to have to use the Biot-Savart law on a test. So he's not going to say, find the magnetic field here, blah, blah, blah. The Biot-Savart law is basically used to find the magnetic field for certain situations, and then you're going to use those formulas accordingly. So it might be, if you remember electric fields, you sort of had a way of finding the electric field due to an infinite line of charge. But once you have the formula for the electric field of an infinite line of charge, you just use it now. So I just want you to sort of know that it's good to know this, put it on your formula sheet, understand how it works. But this is sort of how you derive the magnetic field due to a moving point charge. You're not going to use it very often. Okay. Anyway, so this is Biot-Savart law, how to find the magnetic field. Magnetic field due to a moving point charge. Moving point charge. Cool. So it's going to be mu naught over 4 pi. Mu naught, by the way, is just another constant. It's 4 pi times 10 to the negative 7 is usually how I like to write it, because that way it cancels out the 4 pi. This is similar to epsilon naught, but this is sort of the permittivity constant for magnetic fields. So this is just a constant. Put it on your formula sheet so that you can just plug it in when you need it. So we have mu naught over 4 pi, and then Q V cross R hat over R squared. Again, I know this is a lot. You're not going to have to use this. Just sort of write it down. I'm also going to give you the units for mu naught. It's Tesla meter amps. Just going to put it there. I guess I might as well just say Q is the charge of the point charge. So point charge. V is the velocity it moves with. Now, R is basically the distance between point charge and your point of interest. So basically, if I have a moving point charge, I can find the magnetic field 1 centimeter away, or I can find it 1,000 centimeters away, and that's what R is specifying. Again, write this somewhere. You're not going to use it on the test. Okay. There's one more Biot-Savart law. So this is the Biot-Savart law for moving point charges. There's also one for current. So all that is, again, I'm just going to write it here, but it's not completely necessary. So now that we have a whole bunch of charges moving, we're going to go to an infinitesimal, and you'll have to use an integral to do this. Or I'll write it with the integral. How about that? So the magnetic field due to a current is mu naught over 4 pi integral of your current ds cross r hat over r squared, where r is, again, it's going to be, in this case, the distance between an infinitesimal charge and your point of interest, and ds is going to be the line that you integrate over. I'm going fast on this one because I don't want to spend time on it because you're not going to use it on the tests. But just know, when they came up with all the equations I'm about to give you for the infinitely long wire, the finite wire, all these different geometries, they came out of the Biot-Savart law, but we're just going to use the formulas. So I will just put it here. This is how we got formulas for each geometry. And again, just like electric fields, there are going to be 3 or 4 geometries. Write down the equations for them, and then when you see them in practice, you can just use them. Cool. So that's sort of introduction to magnetic fields. I'm going to give you 3 of the most common geometries where you're going to see a magnetic field. So the first is an infinitely long wire. So I have a wire, there's current moving through it, and I want to say, or I want to see what the magnetic field is at a point P that's a distance A above the wire. So if you use Biot-Savart law, you're going to get that the magnetic field is mu naught I over 2 pi A. So this is the magnetic field at point P. Mu naught is just your constant. This is the current in the wire, units of amps. And then A is just distance in meters above the wire, or distance between the wire and point P. So this is a really, really important one. You're going to use this all the time. It will most certainly be, there will most certainly be at least one question on your test where you have an infinitely long wire. In a situation where he doesn't specify infinitely long, if you hear the words very long wire or something like that, then you always just assume it's infinitely long. I will put in here for finite wire. He usually doesn't do this, but it's good to have just in case. For a finite wire, you'll know it because he'll literally specify what the length of the wire is. He'll say the wire is 10 centimeters. So the magnetic field at a point P above a finite wire is mu naught I over 4 pi A, where A is the distance from the wire to your point P, your point of interest. And then that's times sine theta 1 minus sine of theta 2. And theta 1, theta 2 are just these angles here. If you draw a line from each of the edges to your point P, you'll create 2 right triangles, and then theta 1 and theta 2 are defined as these angles here. So very slim chance that he'll put finite wires on there, but just have it there just in case. Last really important one for me is the curved wire segment. So if I have a curved piece of wire and there's current going through it, and I want to know the magnetic field at this point P, then that's just going to be mu naught I over 4 pi A times the angle subtended by this little arc. Again, this is a very common one. You're also definitely going to see an entire circle. So you'll have your point P and you'll have an entire circle here with radius A. If I wanted to find the magnetic field in the middle, that's just mu naught I over 4 pi A. And then the angle subtended by an entire circle is just 2 pi. So I do my 2 pi. So those cancel and I get mu naught I over 2A. So this is going to be the magnetic field at the center of a current carrying loop. So current carrying loop. Cool. This one's also very popular. Okay. Any questions on that so far? Okay. So again, these are just situations where we have current in a wire and we want to find the magnetic field at some specific point. Notice how, yeah, so Biot-Savart, write it down, understand what it is. But what I really want you to know is that these Biot-Savart laws are how we got the formulas for each one of these geometries. He's not going to have you basically, it's equivalent to like if he had you prove that what these formulas are. Like Biot-Savart law is a way to find what the magnetic field is, but you're just going to use this similar to when you did it with electric fields. He wouldn't have you do that whole integral just to find what the electric field is at some distance from a wire. So write Biot-Savart law down, just know it's how we get these formulas, but you just want the formulas. Cool. Um, One thing you'll notice, so I gave you magnetic field for a long wire, finite wire, and a curved wire. So these three formulas will get you through pretty much the entire test. But notice how I only gave you the magnitude of the magnetic field. I said nothing about direction. So I want to spend a little bit of time here talking about the direction of the magnetic field. And this is when we're going to talk about the right-hand rule. So Biot-Savart law, the Lorentz force, all of that is only going to give you magnitude. So it's only going to give you the magnitude of the magnetic field at that point, the magnitude of the force at that point. But it's up to you to determine what the direction is. And how you do that is what we call the right-hand rule. There aren't 1,000 right-hand rules. There's only one. Now you're going to use kind of you're going to use the same right-hand rule, but there's one you're going to use for point charges and one you're going to use for current. It's the exact same thing, but I'll show you how they differ. So if I have point charges, and I'm just going to give you an example that he likes a lot. So he'll usually do, say, there's a proton here. And this will be like one of the conceptual problems on a test. So here's a proton. We'll say it has like plus q. It's moving with some velocity v. He's going to say something like there's a magnetic field going into the page. Side note, so that you can read this, There's going to be a lot of into and out of the pages here. If you see a circle with an X, that means into the page. So that means the magnetic field, velocity, current, force, whatever it is going into the page. If you see a circle with a dot, that means out of the page. So again, it can be current, velocity, force, magnetic field, doesn't matter. If you see that, that means they want you to know that that quantity is coming out of the page. So in this case, I got a uniform magnetic field going into the page. My velocity is going that way. I want to find the direction of the Lorentz force. And one way he'll specify this instead of saying find the direction of the force is he'll say, is this particle going to go up, down, or stay the same? He'll say something like that. So, all right, right hand rule. It's honestly just easier if you look at my camera. So when I have point charges, I'm going to take my right thumb, and that always goes along the direction of the velocity or just the direction that your particle is traveling in. So my particle is going this way. So I'm going to put my thumb like this. So thumb going to my right, which is your left. So thumb along the direction of the velocity. When I do that, my index finger, I'm going to make a little gun. My index finger tells me basically, oh, sorry, I did this slightly. Yeah, now we're good. So here's my velocity. Now I'm going to put my index finger along the direction of the magnetic field. So thumb velocity, index finger magnetic field, which is pointing into the page. So if you can kind of see that, my thumb's going this way. Magnetic field's going down into the page, like I'm kind of shooting a gun into the page. And then my middle finger, which is going to be orthogonal, is going to tell me the direction of the force. So try and do this on your own page. Thumb in the direction of the velocity. Magnetic field is my index finger. It's pointing into the page. And then my middle finger tells me the direction of the force, which is going up in this case. So I would say the force is going this way. My particle would go up if it moved through this magnetic field. If my magnetic field was going, let's say, for sake of argument, if it was coming out of the page, thumb along the direction of velocity, it's coming out of the page now. So sort of you gotta make your hand work. So my velocity is going this way. Now my magnetic field's coming out of the page. So my force, and you can't really see, but my force is now going down. So my force is now going down if I flip the direction. So the right hand rule, I'll just say thumb velocity, index finger magnetic field, and then middle finger is the force. Cool. Now, when I have a current, I'm going to kind of do the same thing. So let's say we have a wire here. There's current flowing through it. Current is just a charged particle moving with some velocity. So I'm going to put my thumb along the current. And then instead of doing my whole three finger situation, I'm just going to put my thumb along the current and the magnetic field is wrapping around it this way. So if I put my thumb along the current, that means the magnetic field is wrapping around here and it's going something like this. A good way of writing that is it's coming out of the page on this half and into the page in this half. It's kind of like a circle. Cool. All right. Any questions on the right hand rule? Okay. Let's see. Here's law. Mhm. Let me see, my laptop's getting low. Rip. So we got Ampere's law, solenoid. Okay. Let me low key run and get my charger because my laptop's about to die. So give me like 2 seconds. Okay, cool. Thank you. All right, so we touched on how to find the magnetic field in all these situations, how to find the direction. I hope that's pretty clear. Now, last couple things is Ampere's law. So all it is it's kind of like what Gauss' law was with electric fields, Ampere's law is with magnetic fields. So it's a way of finding the magnetic fields in certain more complicated situations. So all it is the magnetic field. If you integrate a line integral, so B dot ds is equal to mu naught I enclosed. So you'll notice it looks very similar to Gauss's law. This is a magnetic field. We're integrating a line integral this time. And then we have our mu naught instead of epsilon naught, and we have I enclosed instead of charge enclosed. So here's just a quick example, which I'm gonna actually have to skip this one as well because I'm running out of time. I'm gonna write this on the formula sheet, and it is in one of the other videos for those of you that want to see it. But just know, here's Ampere's law. He may have you use it, but to be honest, I think he uses it more on the other tests. So write it down. If you want to see me do this example, I'll do it. You can see it in the video, and I'll put it on the formula sheet. Okay. A couple more equations you need to know. Basically just there's a solenoid. Just write this down. If you see a solenoid, there's no magnetic field outside, no B field anywhere.